So do you remember we started talking about the Gauss's law the other day? What I'm going to try to do is show you all different kinds, well, not all, most different symmetries so that it doesn't seem foreign to you guys and it doesn't seem like that scary anymore once you've seen them once and you know what you're doing. So I want to talk about Gauss's law today. And I want to boil it down to three main things that you can do with symmetries. So the first one is whatever charge you have, you can make it into a spherical surface. Number two, whatever charge you have, you can make it into a cylinder, or you can make it into a plane. Now it depends on what charge you have, what kind of material you're given, is what choice of dA you will do. So who wants to tell me what Gauss's law is?
The integral of E dA equals the charge enclosed over epsilon naught.
E dA equal Q enclosed over epsilon naught. Excellent. This is Gauss's law. Now, what is this dA? This determines the Gaussian surface that you have. That dA depends on whether you have a cylinder, whether you have a sphere, or whether you have what is called a pillbox shape. In general, this Q enclosed is written like this, or so what's the first one? Volume. What's the second one? What's the third one? Good so far? Okay, so now let's talk about the different kinds of symmetries that you could possibly have. Let's start with the one we did before. Remember we were talking about this, the line of charge, and we did the Gauss's law. Let's do that really quickly. So the first symmetry that I'm going to talk about is going to be for a line of charge. So I won't spend too much time on this, but I want to remind ourselves really quickly on how we did it. So imagine if I have a line of charge. I'm going to try to make my Gaussian surfaces with orange, just to separate them out. And I'm being asked to find the E at this point. And suppose this distance is R. Then can I write and you remember when we did this, we said that the only surface that matters is the curved surface. The top and the bottom do not matter because E dot dA will be 90 degrees. And cosine of 90 is 0. Excellent. So now may I write this as E R d phi dz equal Q enclosed over epsilon naught. And there should be two integrations. And this is for the curved surface. Or E capital R d phi dz, limits of integration from 0 to 2 pi, from 0 to L, Q enclosed over epsilon naught. So what will be the answer? E R 2 pi L equal lambda L over epsilon naught. Does the symmetry say that the Q enclosed is lambda L, where lambda is the charge density, L is the length? And then this means this reduces down to lambda over 2 pi epsilon naught R. Good? Give me a thumbs up so I can move on to the next one. Excellent. Now, what if instead of having a line of charge, what if I actually had a sheet of charge? So my sheet of charge will look something like this. And let's suppose I choose it to be a positive charge that's everywhere. Now, what kind of symmetry would make the most sense in this case? And suppose I'm being asked to find the E field at this point. Well, can I draw tiny pill boxes and then add them all up? And that might be the Gaussian surface I'm looking for. So one has to go up and the other one has to go down.
Dr. Zane, I'm not understanding your orange square
Okay.
thing right now. I'm a little confused.
Okay. So draw So imagine if this is your sheet. Yeah, this is your sheet. And I'm trying to draw a box on top of this sheet. And then the same box to be at the bottom of the sheet. Okay? Oh, actually, this is a better sheet. This is a better example. This sheet. Okay, and then imagine it again on both sides, right? It can't be on one side, so it has to be on both sides. Okay, so so do we understand the Gaussian surface? And again, it has to be bigger, right, to enclose the actual point that we're looking for. Right, draw it big. And the same surface down. How will I write the Gauss's law for this case? If the area, well, what side matters in this case for the Gaussian surface? Do the sides matter? No.
The vertical surfaces?
The vertical surface is the only one that matters. Very good. So now my dA will go this way, right? That means, may I write my Gaussian surface as and for a Gaussian surface that extends all the way over the sheet, may I just simply write this as EA? Sigma A over epsilon naught. Do you see why it became sigma A? Where it's surface charge density? A's go away, and I am left with so the E field due to a sheet of charge is just sigma over epsilon naught.